Good afternoon and welcome to this Chandrasekhar lecture by David Kaplan. I'll say a few words about David. I think this is his third visit, at least to my knowledge, to India. And I think he has visited the Tata Institute in Mumbai twice, I think. And this is the third visit to the Tata Institute in Bangalore. So David has made pioneering contributions to elementary particle physics and non-perturbative field theory and lattice gauge theories. He obtained his PhD in 1985 from Harvard University. His advisor was Howard Georgi, and after that he was a junior fellow at Harvard, the Society of Fellows. And subsequent to that, he was at the University of California at San Diego, and before he joined the University of Washington at Seattle, where he has been since 1994. And for 10 years, from 2006, he was the director of the very famous Nuclear Theory Institute at the University of Washington. David's research basically in high energy physics, but spectrum is huge. Standard model, cosmology, nuclear physics, lattice, and has made many pioneering contributions to these areas. Especially I'd like to mention that he was an early pioneer in the study of lattice models with exact supersymmetry, how to define non-perturbative supersymmetry on a lattice. And also for a very brilliant idea that allowed us to understand chiral fermions and lattice gauge theories. As you know, this was a very important and still is an important problem. So by introducing a very novel idea in one higher dimension in terms of the domain-wall fermions, and it is a precursor of what many condensed matter physicists work on today, which is called topological superconductors. So for all these amazing achievements, David has been honored. He's a member of the US National Science Academy, the Academy of Arts and Sciences, and also the American Physical Society, and a recipient of various honors, including the Alfred P. Sloan Foundation Fellowship. I'd just like to mention that when he visited Tata Institute in the near past, he actually alluded to the fact that he had a connection with the Tata Institute, which perhaps he was going to mention it, but maybe I'll take the liberty to precede him. His uncle, Bernard Peters, who was a student of Robert Oppenheimer and a very renowned cosmic ray physicist, worked at the Tata Institute of Fundamental Research in Mumbai for 8 years in the early 1950s at the invitation of Dr. Homi Bhabha, who was the founding director of the Tata Institute, for the reason that Bhabha invited him because he was unable to find a job in the United States following the Oppenheimer hearings in which he was accused for some political beliefs. So with these few words of introduction, I'd like to welcome David to deliver his talk on computing reality.
Thank you very much for that kind introduction. It's quite an honor and pleasure to be here today. And I assume that, like most people here, my path to becoming a scientist was sort of illuminated by certain discoveries along the way about existing science. And one of the brightest moments for me was as an undergraduate learning about Chandrasekhar's theory of white dwarfs and neutron stars, because it just struck me as incredibly beautiful that you could have these enormous stars that are supported by quantum mechanics. So this is one of those brilliant ideas that just kept me going in science. And of course, it got reinvigorated last year when we learned that these marvelous objects are very likely to be the origin of the heavy elements that we're made out of and that the Earth's made out of. So it's an extreme honor for me to be invited to give the Chandrasekhar talks. So usually for a scientific colloquium, one chooses some sort of piece of physics that has had recent advances and future, and you sort of summarize it and present nicely tied up package for the audience. I decided to do something slightly different, which is I'm going to give an ode to to computational physics. I won't burst into song, but I have a agenda here, which is that I think there's often a misunderstanding about what computational physics is, which is sort of demonstrated by this picture where you have a few great theorists who come up with great theories, and then they sort of drop it down on the hard-working computational physicists who are down there with their hard hats, who have no hope for recognition, and who just toil away trying to make sense out of these wonderful theories. In fact, when I was an undergraduate, I had a very famous experimentalist as an advisor, and he told me, don't go into theory. There are no more than 5 theorists who ever make a contribution to the world at any given time, and you're probably not going to be one of them. So, but I was strong. I withstood his advice. So I don't really buy this model of computational physics, and I want to actually stress and give examples for why I consider this to be a very important part of physics that's a place for great creativity and which greatly deepens our understanding of physics. So I'm going to do this with just sort of 3 vignettes of physics, and of course computational physics is a vast subject of which I'm familiar with a very small corner of it. And so I'll be focusing on that small corner, but I think some of the lessons are more general. So the first vignette is the study of nothing. The second one is chirality, extra dimensions in topology. And then the third one is the study of something. And I will explain what those mean as I go along. So first, the study of next to nothing. So, as you all know, electromagnetism is a theory of photons and charges, and one of the key features of photons is that they do not couple to each other. And that means that if you find 2 solutions to Maxwell's equations, you can add them up and you'll get another solution. And so wave solutions can be superimposed, and that even though electromagnetism seems sort of difficult the first time you meet it as an undergraduate, it's actually one of the simpler theories we have. In contrast, the strong interactions are described by gluons, and their characteristic is that they carry their own charge, and so they stick to each other, and therefore solutions cannot be superimposed, and the nonlinear interactions, as usual, make the theory extremely complicated. So, how do we think about gauge theory? So this is how Maxwell thought of electromagnetism. And I'm going to suggest that this is actually how modern physicists often think about Yang-Mills, something very similar. Though I don't know quite why Maxwell preferred a honeycomb lattice. It looks a little bit complicated. But that's how he thought of electromagnetism propagating through empty space, because he couldn't quite develop a picture for empty space. And this will be part of my lesson, is that empty space is really not so empty after all. So Wilson is the person who really took the bull by the horns and said, we want to understand this theory, and there's just so far we're going to get with models, and there's only so far we're going to get with pen and paper. Let us put this on a computer. And the problem that you immediately face is that space-time is continuous. There are an infinite number of degrees of freedom in the theory. We have to cut that down to a finite number so that a computer can deal with it. And so he suggested turning space-time into a lattice of points. So then what do you do with those lattice points? Well, we're going to put some fields. Fields are now like quantum mechanical variables that live in all these lattice sites and lattice links. And then we'll use the machinery that Feynman developed, the Feynman path integral, where we will sum over paths through field space weighted by the exponential of the classical action. And when you do this, this integral should give you all the information contained in the quantum field theory. And so by putting this on a lattice and performing this integral, we've reduced quantum field theory to the task of computing a very, very large but ordinary integral in terms of many, many variables. So when you do this with QCD on what's now considered a relatively large lattice, you end up with millions of degrees of freedom. And so you need a supercomputer. Now, I just want to clarify that these paths here, they look like particles moving through space-time, but the way they're actually done for lattice QCD, those paths represent paths through field space, and so every path is itself a very complicated-looking gluon distribution, such as this one here. And so that's what a typical path might look like. So this begs some questions, though. You know, this lattice does not look like space-time. How do we end up getting something that really represents the quantum field theory we're interested in, continuous spacetime. How can a computation that is necessarily finite work on a quantum field theory which was notorious for almost producing infinities? I mean, you know, when you're doing a calculation, you can write an 8 on its side, that's no problem. But when a computer hits infinity, you know, smoke comes up. So you don't want that. So the question is, how does this theory actually deal with those infinities? And what is renormalization when you're doing a computation like this? And then there's the question, what is the gauge symmetry? And how do we understand phenomena such as confinement and chiral symmetry breaking of quarks from this rather distant-looking theory that doesn't look like the mesons and baryons that we actually see in the experiments. So all these questions can be studied even without looking at excited states of QCD, but looking at the vacuum, which is nothing. So it looks like nothing to us because we're like fish in the water, okay? But this poses a PR problem, even though there's a lot of physics in the vacuum. If you ask for money, it's sort of embarrassing to say you want to study nothing, because most people think of nothing as, you know, the thing that astronauts are trying to avoid, which is the most boring substance in the world, but which is inimical to life, while the physicist sees this as a seething, complicated thing. So Wilson took inspiration from condensed matter physicists, which is that you don't really want to study the water you're in. You want to look at something that you can poke and prod. You can change the temperature, the pressure, things like this. So the analogy then is with condensed matter physics, where you have a sample that you can change all the parameters in and see what it does without actually crawling inside it. So one of the first questions then is that if you were trying to represent lattice QCD by this quantum field theory with a lattice of points, one of the basic questions is, how do you return to continuous spacetime and all of its symmetries in the limit that the spacing goes to 0, such as translational symmetry? See, this lattice doesn't have translational symmetry. You can only move in discrete jumps. Rotational symmetry. Well, this lattice here only has rotations by 90 degrees, and we want to be able to discuss physics at other rotations. You know, when you do a collision in a collider, you don't see Bragg spots, right? So the way a crystal does. So how do you recover the limits you want in the limit that the continuous spacetime, the limit that you take your lattice spacing to 0, and not just end up with continuous spacetime, but you want all the symmetries like rotational symmetry and translational symmetry. So we sort of have an intuitive feel for that because, of course, this wood and the chair, everything around here we know is made up of point-like atoms, but it looks like a continuous medium to us. But we're sort of cheating because we're taking light, very long wavelength, and bouncing it off the surface. We're not actually using the excitations in the material to study it. So Wilson told us that we should let's think of the lattice spacing as fixed, and let's require that the physical particles that we want to have live on this lattice actually have very long wavelengths. So that when the wavelengths are very long, they sort of see an average over the whole lattice, and they're not so sensitive to the discrete nature of the lattice. Now, if you're talking about a condensed matter system and you're asking, how do I make a condensed matter system have very long wavelength excitations in it, then typically it usually only occurs near second order phase transition. So going back to that experimentalist who's got this material in that cryostat and poking and prodding it, you want to change the parameters to the point where you have a second order phase transition. So for example, if you look at some cartoon of a phase diagram, say for water, we know that if we're at atmospheric pressure and we start off with liquid and we heat it up, temperatures on this axis here, we're moving sideways, we cross a phase transition where the thing starts to boil. And when you boil water, the size of the bubbles sort of has a characteristic length scale, and this corresponds to a first order phase transition. This is not what you want for the lattice theory. You do not want a characteristic length scale that is fixed, maybe say 20 times the lattice spacing or something like that. You want wavelengths that become infinitely long compared to the lattice spacing. So what you could do with water is you could change the pressure. You could increase the pressure. Now, instead of crossing the line here, you cross it at this point E, which is called the that's the critical point, where the first order phase transitions end on a second order phase transition. And when you boil water here, the bubbles appear on all length scales, and you can have very long correlations in your system. So we're saying then that the vacuum for QCD is sort of like a condensed matter system, but a very special one that's been tuned very close to a second order phase transition. Now, of course, these constants are finite. what constant we're talking about. Maybe we're talking about the gauge coupling constant. Maybe we're talking about some Yukawa coupling constant, something like that. All these constants that we're giving the computer, though, are finite numbers. So there's no manipulation of infinities in this procedure. This is some street art I found in Rio. This is actually like 3 meters high, painted on the wall. I think it's supposed to be a politician, but for me, it's an old-time physicist, okay? So the way people were doing quantum field theory before Wilson is they were renormalizing the theory, meaning that they were trying to hide infinities. And they were pretty good at it, but they always felt very bad about doing this. And you can tell when they talk about it, they sort of hold their heads and they say, yeah, we can do it, but isn't this awful? And I recall hearing from Pierre Ramon told me he once went to a lecture where Dirac was, and afterwards he went up and talked to him, and he tried to talk to him about quantum field theory, and he was shocked to find that Dirac found the whole program of developing quantum field theory had been a failure because of the renormalization. And he just thought that these infinities meant that the whole 50 years of work was wasted somehow. So in this old way of looking at things, the good theories are the ones where you find a place to sweep all the dust, all the infinities, and the bad theories are the ones where you cannot find such a place. Now, with Wilson's view, that changed completely. So renormalization gets replaced with tuning the lattice parameters in order to find the second-order phase transition. Good theories, therefore, are ones where you can find a second-order phase transition. Bad theories are the ones where all you find is, say, first-order phase transitions, because then the correlation lengths never get longer, very much longer than the lattice spacing, and there is no continuum quantum field theory corresponding to that. It's all very much a lattice theory. Now, often you can get theories that look bad, but then you can embed them into a larger theory. So, for example, if you try to study quantum electrodynamics, and you really wanted to make the correlation length go extremely long compared to lattice spacing, you would find that it's a bad theory, because at some point you would not be able to change the parameters any further and keep on making the correlation length longer than the lattice spacing without turning off the interactions completely. On the other hand, you can embed the quantum electrodynamics in a bigger group, like grand unified theories, and then the theories become healthy again. So often, what looks like a bad theory is really just the low-energy version of something that's more complicated, that it does have a second-order phase transition. And finally, there's a term here. I don't know what the official term for such theories is. I call them peculiar theories. These are ones where second-order phase transition is possible, but it requires an incredible fine-tuning of parameters. So we don't really know that these are bad theories, but there's a feeling that they're bad theories. And in fact, much of the physics much of theoretical particle physics for the last 30 years has been trying to figure out how to not have these theories that require incredible fine-tuning in order to find the phase transition. Now, this is sort of a philosophical point, and with the discovery of the Higgs, which is exactly one of those theories, we now are starting to question whether all that effort was worthwhile, and maybe our distaste for these peculiar theories is misplaced. In any case, this development from Wilson's work on putting quantum field theories on the lattice really turned particle theory on its head. So now, renormalization, instead of eliminating infinities, just means finding the coupling constant trajectory for tuning the theory to a second-order phase transition. QCD became the prototypical good theory, one which had exactly the type of phase transition you're looking for, and it does it weak coupling. QED, which had been the prototypical good theory before, now becomes potentially only an effective theory because you can't find a good phase transition. And Fermi theory, which everybody had agreed was bad, but it also had agreed that they would use it, turned out to be actually quite a good effective theory, which then got embedded into the larger standard model. And then finally, the Higgs in the standard models I mentioned, it was considered a very good theory, and now it's one of those peculiar theories that's incredibly fine-tuned, and we don't know quite what to do with it. So, other insights. So, Wilson put quarks on lattice-sites, and put gluons on links, and the gluons were put in there for a specific purpose in order to let the quarks have independent phase rotations without changing the action of the theory. So in this sense, a gluon is like the differential in a car. The early cars, when they went around corners, had a problem, which is that the wheels on both sides of the axle were forced to rotate together. But the inner wheel was going on a shorter path than the outer wheel, and that meant that the ride was incredibly rough. And then some engineering genius, probably smarter than anyone in this room, invented the differential here, which allowed the power to go to the wheels, but it delivered the power in such a way that the inside wheel could turn slower than the outside wheel without them being rigidly attached. And that's what the role of the gluon is in this lattice here. It allows the quarks to rotate independently. Now, in quantum mechanics, if you had a phase which is free, like a particle on a hoop of wire, the ground state is incredibly boring. It's just an S wave. It's a constant wave function all the way around the circle. It's about the most uninteresting wave function there is. Now we've got all these phase degrees of freedom associated with every single quark on the lattice, and you might think that, in fact, QCD, therefore, is very boring. So, is the ground state of gluons trivial? Well, almost. If you coded up Wilson's theory with the quarks and the links, and you forgot to put in a line of code to integrate one of the links, it wouldn't make any difference at all. You'd get exactly the same answer out at the end. You could have forgot 3 links, 4 links, whatever. And for many, many choices of links that you forget, you would get exactly the same answer. It turns out that the only combinations of link variables that actually have some physics in them are the ones where the product of the links are taken either around a closed path or else ending on a quark or an antiquark. Lines of gluons which just sort of start somewhere and end somewhere else, all of those links could have been abandoned from the integral and you would never have noticed. So once you see this, then you can start asking, well, it's sort of strange. We paid a huge price in order to have a beautiful Lorentz invariant-looking theory made out of gluons, which have 4 components, vector potentials and so on, when in fact the degrees of freedom of the theory are vastly different than what we're putting on, and in fact there are far fewer in some ways than what we've put on the lattice. And so Wilson was able to then address various physical questions about QCD, such as what is the nature of confinement, by looking at these closed paths and asking questions about that. In particular, he showed that even in QCD without quarks, you can study the nature of confinement by looking at how these closed paths, how their energy goes as a function of the size, and then he showed that they fall off exponentially with the area, and that would be a sign for confinement. And then people have numerically confirmed that that is indeed how QCD behaves. So, by putting QCD on a computer and asking, how do you actually take this theory, take it really seriously, so seriously that you get numbers out, he changed how people think about quantum field theory completely. Gave us the renormalization group, along with advances in condensed matter theory, effective field theory, our present understanding of confinement, and so on. We're used to telling our students, you won't understand this theory until you calculate something. And usually what we mean is there's this well-defined theory, and they just have, they've absorbed the words maybe, but they don't know what it means. And when you do a calculation, you say, aha, now I know what it means. But here at an even more fundamental level, the theory that we had didn't even really make sense completely. And only when you're forced to put on a computer are you forced to actually make complete sense out of the theory, because the computer doesn't give you the freedom of being sort of wishy-washy and confused about things. So my next chapter, or anecdote, or the next 2 actually, concern places where Wilson's theory fails to solve the problem. And the first place has to do with chirality. So as far as I can tell, the story of chirality actually begins with Louis Pasteur, who was hired by the wine industry to try to figure out why some wines went bad and some ones didn't. And he was a young scientist who was very inquisitive, and the first thing he did was he took some wine and he evaporated it and looked at it under a microscope. And he discovered there were a lot of crystals there. There was tartaric acid. And he also noticed that the crystals had this peculiar asymmetry, and that you could divide the crystals between left-handed and right-handed crystals. And he did that with tweezers. And then he dissolved these crystals in water, in separate water, beakers. And then he shined polarized light through them and found that the polarized light rotated in one direction with the left-handed crystal water and the other direction from the right-handed crystal water. So this is the beginning of chiral chemistry. Chiral is just the Greek word for hand. So chirality exists in particle physics too, with fermions. In particular, if you had a fermion, you could define something called the helicity, which is if you take the momentum and you dot it in with the spin, you'll either get a positive number, in which case we say it's right-handed, or a negative number, in which case we say it's left-handed, except I might have gotten the convention wrong. But, the problem with this definition, though, is that it isn't the same for all observers. So if you come along in your Battlestar Galactica fighter plane and you're going extremely fast, and you look at these particles, now to the observer in this extremely fast rocket, both particles look like they're going backwards because the rocket's going faster than both of them. But the spins, of course, haven't flipped. But now this looks like it has a positive helicity, this one looks like it has negative helicity, so it's changed. So it looks like helicity is not a very fundamental thing here, except there's one exception, which is that if these particles were massless, they'd be moving at the speed of light, and there's no way that this rocket could ever overtake them. And so for the massless particle, this rocket will always agree in any frame what the helicity is of these particles. So when you have massless particles, the helicity is called chirality, and it's a conserved quantity. You can make interactions which violate it, but for at least a free particle with which is massless, and gauge theory in particular, also, there's a conservation law called chiral symmetry. And you can also extend that to talk about approximate chiral symmetry. And chiral symmetry turns out to be an extremely important feature of QCD, which has a lot to do with the phenomenology that we see. So this is a picture of Nambu, and he was fascinated by the BCS theory of superconductivity, in which the ground state for a superconductor is a very complicated ground state, very different than what particle theorists had been thinking up to then. Up to then, a ground state was just a little bit of 0-point fluctuation on a harmonic oscillator, but what they found for the BCS theory was a highly correlated state where the electron pairs condensed into the ground state. So Nambu suggested that the universe might have a similarly complicated vacuum filled with, well, I want to say quark-antiquark pairs. I don't actually know how he thought about it, because he did this before quark theory was really, certainly well before QCD. But he thought of it as a condensate of fermions, and he showed that this would break chiral symmetry, and that when you break a symmetry like chiral symmetry, you produce light Goldstone bosons, and he said that those could be the pions, and that would explain why pions are so light in QCD. This is actually the accepted view now of why pions are so light, and it shows that if you really want to understand the phenomenology of QCD or nuclei or anything, you have to understand how the chiral symmetry works. Unfortunately, straightforward approaches of putting particles on a lattice, like Wilson's, automatically destroy the chiral symmetry, and they do so not because just a little technical fix being needed, but rather for a deep reason. So the reason that the way I like to think about it is that the reason's due to something called the anomaly. So imagine you have a wire, and you've got Dirac fermions living on the wire, so they live in 1+1 dimensions. And so the dispersion relation, if I solve for the energy and momentum of these particles, just free particles on this wire, I get a little plot here where the vertical axis is energy and the horizontal axis is momentum. And so you get an infinite number of states in either direction. And according to Dirac, who first discovered all these negative energy states, he said we should fill them up and call that the Dirac sea. And so when all of the states are filled up to this midpoint here, that's what we call the vacuum. And so what's pictured here is not the vacuum, but on top of it, it's got a number of right-handed particles. The blue states are filled above the horizontal axis. And we also have some left-handed particles. I call them left-handed because their momenta are negative. They're moving to the left, which are living above the axis there. And now let's turn on an electric field to the right. And we know from undergraduate electromagnetism that when you have a particle of charge q and you turn on an electric field, it feels a force, and therefore in a time dt, its momentum will change by an amount dp, which is just the charge times the electric field. And what that means then is that all these states are going to start marching off to the right. And the blue ones, as they march off to the right, they're forced to go up their dispersion line, up this way. And the red ones, as they're forced to march to the right, they get pushed down along the red line. And so you see that the blue ones are being pulled up out of the vacuum because you get more and more of these blue states, but at the same time you're getting less and less of the red states. So luckily, charge is not violated because the red ones are going into the vacuum just as fast as the blue ones are coming out of it. But if you calculate the change of the number change of the right-headed modes, you'll find it's dp over 2 pi because they're coming out. And if you change it in left-handed, they're going in, so it's negative. So if I add the two, I get 0, and that's good. That means I'm not changing the charge of the world. But if I subtract them, I do find that the chiral charge, the chiral symmetry charge, is changing, and it's proportional to the electric field. And this is called the 1 + 1 dimensional anomaly because it's an anomaly because if I actually look at the Lagrangian for this system, it looks like the chiral symmetry should be exactly conserved. This has a generalization in 3 + 1 dimensions where what changes instead of the electric field there is you have electric field dotted in with the magnetic field. So a key feature of why this happened was this infinite source and sink for fermions here, where fermions could keep coming out of the vacuum or keep going in. So in the continuum, chiral symmetries of the classical theory can be violated in the quantum theory due to the infinite Dirac sea, which is not possible on the lattice. So there's got to be some big difference between QCD in the continuum and a lattice QCD. So what's going on in the continuum is the famous Hilbert Hotel. You have a busload with an infinite number of people, or infinity of infinity. He has a whole long story there, which comes to this hotel, which is completely full, but luckily it's infinitely large. And it says no vacancies, but they convince the concierge to move everybody down in their room by 1, and that opens up a space. And then they move everybody moves down by 1 again and opens up another space. And pretty soon you find that this full hotel is able to accommodate everybody who's on the bus. But there are no infinite hotels on a computer, so what happens? On a lattice, you find that the dispersion relation for the fermions looks quite different than it did in the continuum. Well, not for all fermions. If you look at the low momentum fermions, which are the long wavelength modes, their dispersion relation has that same X-like pattern that we saw in the continuum. But when you start looking at momenta where the wavelengths are on the order of the lattice spacing, the dispersion relation curves around. So now when I turn on the electric field, these red states are being pushed down, but they pop up on the other end. And likewise, when I pull out the blue ones, they're getting popped down on the other side. So when I try to do the anomaly calculation on the lattice with this theory, I find I get 0. So this is a fundamental problem because you've got this lattice theory, it's supposed to represent the continuum theory, and they're giving different answers for any size lattice spacing. So it turns out a solution for this is to formulate QCD in 5 dimensions. So let me describe that. So this goes under the name of domain wall fermions. So imagine a world, instead of talking about 5 dimensions, I'm going to say I want to study a 2-dimensional world, so I'm going to go to 3 dimensions. So here's the 2 spatial dimensions, and I can't draw time on this, but you can imagine a particle living on this sheet, which extends in infinite direction in one spatial direction, and an infinite amount of time, and a finite amount in the extra spatial dimension, which I'll call y, and so it's got edges on it. So I put fermions down on this, and I give them a big mass. When I do that, I discover that the theory has solutions where I get massless modes, or almost massless modes, stuck to the edge of the boundaries there. They become massless in the limit that the size of the strip becomes very wide. Well, in the bulk of the sample, the fermions are very heavy, because I gave them a big mass. Now, if I apply an electric field here, I find that one side, the fermions get depleted, and the other side, they build up, and that there's a current that goes across here. And in fact, it's very analogous to the quantum Hall current. Now, you might say, well, how could this be quantum Hall current? I didn't put a B field here. Well, it turns out that for Dirac fermion, the mass plays the same role as a B field does in a condensed matter sample, because masses, strangely enough, in 3 + 1 violate time reversal symmetry. So you find massless modes. If I now go to the analog, where this is a 5-dimensional strip and these are 4-dimensional surfaces, then you find massless modes on the 4D surfaces, left-handed on one side and right-handed on the other. And then if I look at low energy physics, the massive bulk modes decouple, but they leave behind a remnant of chiral symmetry breaking, which is just right to allow these currents to flow from one side to the other, and it reproduces the anomaly correctly. So this is a theory that breaks chiral symmetry in exactly the right way at finite lattice spacing to reproduce the anomaly in the continuum. Furthermore, the interesting thing is that this effect is what's called topologically protected, meaning that you don't have to be ultra careful on how you design your lattice. So if this is the analog again for a physical sample with the quantum Hall effect is, you don't have to, if somebody told you that the quantum Hall effect wouldn't work if there were a few stray atoms in your crystal, or there's few dislocations, or maybe your fields were not quite uniform, yeah, it wouldn't be very interesting. But in fact, these systems, both the condensed matter system and this lattice theory, are topologically protected, and you don't have to carefully fine-tune the lattice interactions. So how does that work? It seems counterintuitive that a lattice could have topology. After all, topology is a property of continuous manifolds. A lattice is not continuous. Well, on an infinite lattice, it's true that space is not continuous, it's a lattice, but the momentum space is continuous. In fact, momentum space is described by the baryon zone, and it's a torus if you have periodic boundary conditions. So you have periodic boundary conditions in momentum, represented by a torus. You can cut the torus along these circles, and it opens up like a square, where the magenta circle here are these two magenta lines, so you have to think of these as being identified with each other. And then this circle here gives you the red lines, and those have to be imagined to be identified with each other. And fermion's momenta lives on this continuous torus. And when I solve the Dirac equation, I find that they have a dispersion relation, energy-momentum relation in the bulk. And it turns out that the dispersion relation maps you from a particular energy-momentum onto a d-dimensional sphere. And that sphere has to do with the orientation of spin as you move it around in momentum space. And this map can be non-trivial. So for example, one way to map the torus onto a sphere is I could take this square and I could just shrink it down to a point and put it on the North Pole. Or equivalently, I could take this torus and just mash it up against the surface of the sphere and say every point where the torus touches or wherever it lies above the sphere, I'll map it onto that point in the sphere, and then I just sort of scrunch that torus down to a point on this point here. So that would be a trivial map, where sort of the torus is outside the sphere and gets put down on its surface. A less trivial map is if I take this square and I wrap it around the torus and then seal it up at the top. Or equivalently, if I put the sphere, if I were to cut open this torus, stick my sphere inside and then sew up the torus again, then sort of shrink wrap the torus onto the sphere. That's a non-trivial map. And it turns out that the winding number of these maps are integers. They can't change continuously. And the number of massless modes that live on the surface are related to these winding numbers. And because the winding number can't change continuously, that means if I just change parameters of my theory a little bit, say the mass or gauge coupling or something like that, it can't change the number of zero modes on the surface. So this is the physics that guarantees that the Hall current is quantized, and why you're able to, for example, measure the fine structure constant so precisely looking at the quantum Hall current without having to guarantee that for 10 digits of accuracy in alpha, I need to have 10 digits of purity in my sample. These quantized phenomena can only change if something drastic happens in the sample. And in this case, that something drastic is that I change the parameters so that for some reason the gap, the energy, the mass of the particles in the bulk goes to zero. So as I change parameters continuously, once I pass through these special points where the bulk becomes gapless, that's when the number of zero modes can suddenly change. So the Riemann fermions, therefore, are examples of what are known as topological insulators in condensed matter physics. And so, for example, the quantum spin-Hall effect, which was discovered in 2004 by Kane and Meili, was actually also realized as when in discussions of chiral gauge theories about 12 years earlier. Namely, here's a strip of material, and it's got a Dirac fermion on both sides. And what's special about this system is that when I turn on the electric field here, I can get a Hall current, but the Hall current does not carry electric charge, because the electric charge for the red fermions goes one way and blue fermions goes the other, and they cancel out. But spin does get transported through the bulk, and so that's why it's called the spin-Hall effect. This is a particular example of a topological insulator that was, I think, theoretically suggested by Zhang from Stanford, called stannine. It's graphene with some tin atoms, and it was first synthesized at the Indian Institute for Technology just a couple of years ago. So, strangely enough, many simulations of QCD today are not performed on the original lattice that Wilson suggested, but have escaped off into the fifth dimension, and where the world is modeled as the four-dimensional surface of a five-dimensional topological insulator. So another problem that arises when you try to do quantum chromodynamics on Wilson's lattice is when you start looking at matter. Now, of course, we're interested in matter. We're made out of matter. We don't want to just study the vacuum. So how can we understand questions such as, with Chandrasekhar's neutron star, how does it actually look like in the middle? Are there strange quarks there? How dense is it? What's the radius? We've got a theory of the strong interactions. We'd love to answer these questions about these strongly interacting particles. So QCD has had, lattice QCD is, following Wilson's program, has had many great successes for studying matter if you don't look at too much of it. So here, for example, is the state of the art, or I think pretty close to the state of the art, of the mesons and baryons in QCD. Here are their names, and here's their mass. And a few of these are put in by hand as calibration points, and everything else is computed, and the lines there are the experimental values, and the dots are the result from these computations. So you can see this is fantastically accurate. At this point, I want to take a just short historical digression because there's some history here that some of you might be interested in that you are unaware of, which is that a large number of these particles appearing here, much of the early work on their discovery occurred in the TIFR at Mumbai with these balloon experiments. Here's a photograph from the 50s of the balloon experiments where they would send photographic emulsions up into the atmosphere and look at the cosmic ray tracks of the particles that are produced in the atmosphere. In 2005, one of the participants of these experiments, Yash Pal, wrote down a historical reminiscence, and it's sort of exciting just to read it. He says that we found that there was another funny particle produced along with it. And it turns out this funny is what is now known as strangeness. So it became clear that somehow one funny requires another funny to be together, and once they separate, then they are acting differently. So there's another property. This came to be known as strangeness. Just a few months later, Gell-Mann used along with the term associated production. In a sense, I would say that associated production of particles was first discovered in this lab, TIFR. We didn't call it that, but we remarked on it, and of this type, so many are produced together, and that was a very important insight and recognized the world over. He said, look, the total number of strange particles in the world at the time was about 20, and about 8 or 10 of them were discovered here. Then the whole world changed. That was actually physics of that era. Sounds like a tremendously exciting time. So I think that these are probably the particles that they were seeing. Well, so you go on. You want to do, mesons are great, but we're not made out of mesons primarily. We'd like to see baryons. We'd like to see nuclei. Once you get even to the lightest nuclei, you run into trouble. So here's a brave calculation of the triton binding energy. The triton's bound by just a few MeV, really, compared to a mass of a few GeV. So you have to do quite a precise calculation to extract this number. And what you're looking for is a plateau here in the dots. But you can see there's just sort of a small region where there's a plateau, and then they get completely decimated by noise. And this is a hallmark of looking at systems with a large number of baryons in lattice QCD using Wilson's lattice. So the triton is bad, the alpha particle is much worse. There's no hope of ever doing iron with current technology. This noise becomes exponentially bad with the number of nucleons. So what's going on? So remember we talked about looking at this lattice with these millions of degrees of freedom. Now, millions sounds like a lot, but it's not the true number that's behind this system here, this is a quantum system, okay? So we should be talking about the size of the Hilbert space, which is e to the millions, okay? So this is a huge Hilbert space. And so lattice QCD is doing a stochastic sampling of gauge field configurations along those paths. And you might ask, how in the world were they ever able to get anything out of this calculation if that's the true size of the system? Well, if you have a 1D wave function that looks like this, you can do a sampling, and you can get a pretty good estimation for it by doing a relatively few number of samples. 2D wave function, again, this wave function, nice and smooth, you can get a pretty good sampling and get pretty accurate wave function matrix elements by doing a relatively small number of samples. And so what happens is when you are looking at this huge dimension wave function for the vacuum, as long as the ground state is relatively smooth and localized, a stochastic sampling in the path integral will be able to do a pretty good job. Now that seems like an incredible naive wish that the ground state of QCD would have this nice localized shape, but in fact it does, and that is why at zero baryon number, you're able to get quite good matrix elements for the vacuum properties and the low excitations of QCD. But when you look at systems with with a large density of baryons, then in fact the system seems to be quite different. That the wave function has an is incredibly complicated and highly correlated. And since you're starting off with the wrong degrees of freedom, you're starting off, pointing in the wrong direction in this vast Hilbert space. And you have to find your way to the right direction. But the Hilbert space is so large, and the correlations of the true ground state are so far away from where you started, that it becomes an exponentially hard problem. So it seems like you need an exponentially large number of samples of the wave function to be able to approximate it. Here is an estimate. This is now pretty old, but the numbers involved are so extreme that it doesn't really matter whether this is up to date or not. So here what I've got is a box size in fermis. A nucleon is roughly a fermion size. You'd like to look at, forget neutron star, which is 10 kilometers across. Let's just be happy to go up to 5 fermis across, okay? And on the vertical axis is floating point operations, and these numbers probably don't mean much to most of you, but this dotted line here is 1 year on an exaflop's computer, exaflop being about 10 times faster than the current fastest computer. And then I've got these colored lines here, and the different colors correspond to different temperatures. It turns out that the hotter the material, the easier it is to simulate it with it. So here, the lowest one is 10 MeV, and that's still pretty hot because excitation levels in nuclear are in the order of 1 MeV. So you'd really like to study cold nuclear matter at neutron star, which is way lower than 10 MeV. But let's settle for studying 10 MeV nuclear matter in a relatively small box and ask how hard it is. And what you find is that if you go to a temperature of 10 MeV and a box that's very small, 3 fermis, and you want nuclear density in that box, if you use this graph, you have to sort of extrapolate. You end up with something like some huge number of exaflop years. It is way beyond our capability of simulating this through a brute force approach, and obviously it gets way worse if you start looking at more interesting problems. So apparently the problem is the vast size of the Hilbert space and the fact that these ground state wave functions are super highly correlated and very complicated. So classical computers are ill-equipped for these problems. So something that's becoming of topical interest and right now is whether quantum computers will come to the rescue. And the answer is not known, but there's a lot of interest in this right now. So what is a quantum computer? So a classical bit, is just a register, which can be a 0 or a 1. A quantum bit is a spin. You can model it with a spin half particle, and you can see that it could be 0 or 1 corresponding to spin up or spin down, or it could be spin pointing off to some other direction, like a eigenstate of sigma x, and then it would be a linear combination of spin up and down. But that's not where the real interesting part of a quantum computer comes from. If you look at 2 classical bits, so here's one state, 0, 0, and here's another state, 0, 1. You can get from the first one to the second one by a bit flip, a single bit flip, which you can think of as a 2x2 matrix acting on a state which is 0, 1. And so, in fact, you can obviously get from any initial state to any final state by a sequence of such single bit flips. In contrast, if you had 2 qubits in a state 0, 0, or else in this correlated entangled state 0, 0 plus 1, 1, this is sort of like the Einstein-Rosen-Podolsky state, you can obviously not get from here to there by flipping 1 bit at a time. In fact, to get from here to here in this Hilbert space, you can do it with a unitary matrix, but it has to be a 4x4 matrix. This is because of what's called entanglement, the fact that the 2 bits are correlated. So in fact, for n classical bits, I could get from one string to another by a product of n 2x2 matrices. On the other hand, for n qubits, I need a 2 to the n by 2 to the n matrix to get from one to another. So there's a vastly much larger amount of information that can be stored in qubits because of these correlations and entanglement. So if you have a classical bit stream like this, then you can encode a book. And you know that if you tear out 1% of the pages or rip out 1% of the registers, you will lose 1% of the information. If you have a qubit stream, what happens is these are all entangled, and the information's in the entanglement. So if you open up your book, what do you see? Nothing intelligible. One page contains no information, basically. If you tore out a page of that book, you wouldn't lose 1% of the information. It'd be more like as if you had a photograph and you reduced its resolution. You couldn't say at any one point that the information's changed very much, but the overall information in the picture would change a lot. So one page has information about what's on the other pages. This is what Einstein called spooky action at a distance. So a quantum book contains vastly more information than classical books. If you have 300 qubits, the amount of information you can encode there is roughly the same as what you'd need 2 to the 300 classical bits to encode. That's more than the number of degrees of freedom in the universe at the classical level. So the question is, you got all this power, can you use it? So on a quantum computer, how do you use it? You initialize some qubits, you evolve it with a Hamiltonian, unitary evolution, which you construct out of a series of gates that act on the qubits, and then you measure matrix elements in the final state. So algorithms on a quantum computer look very different than on a classical computer, and they're really changing how we think about doing computations. So for example, the example I want to discuss just briefly is how do you address a very simple problem, which is if I gave you a Hamiltonian, how do you find its ground state? And so for example, suppose you want to find the ground state of the Hubbard model for high-TC superconductors. Whoops. Sorry, wrong button. So I'll give 2 examples just to show you how weird programming on a quantum computer is. The first one's called the quantum phase estimation algorithm. The second one's called the quantum adiabatic algorithm. So suppose you've got an eigenvector of some unitary operator. It'll be modeled. I'll be modeling e to the minus iht, namely the Hamiltonian evolution. But let me just say it's got some eigenvalue e to the 2 pi I theta, and I want to determine theta accurately. This will be eventually like determining the energy. Suppose I want to compute it to an accuracy of 1 part in 2 to the minus n. Well, so the way you do it with this quantum phase estimation algorithm, you induce n auxiliary qubits, and then you entangle them with n applications of your unitary operator. And then, in the end, you measure the auxiliary qubits. And this measurement will give you a probabilistic measurement of theta to high accuracy. The probability is highly peaked around the value of theta, where the values of the auxiliary qubits are the value of theta given in a binary, as a binary number. This can be applied to a general eigenvector, not eigenfunction, not an eigenvector view, but eigenfunction. And what you will do is if you keep on measuring the output, repeating the experiment, and measuring your qubits, you'll get a bunch of numbers, and if you plot them versus the number, a histogram, you will end up with a spectrum. And the height of each peak will be located at one of the eigenvalues of h, and the height of the peak will be proportional to the overlap of your initial wave function with that eigenstate. Well, that's a little bit vague and confusing sounding. This is what it looks like. Here is a picture. So a program for a quantum computer looks like a musical score, and it's called a score. So here we have a set of m qubits that is programmed with my initial guess for the wave function. And here are my n auxiliary qubits that are initialized at 0. The first thing is you apply what's called a Hadamard gate that turns every 0 state into a linear combination of 0 plus 1. So now the wave function, after you've applied these gates, which correspond to just rotations around the x-axis of your spins, you end up with this wave function, which is more complicated, but it's not entangled. It's just a product state. But now you've got all these strange things here. These are called controlled rotations, or controlled gates. The dot means you first measure this qubit. If it's a 0, you don't do anything. And if it's a 1, you act with this operation. And this operation says apply the U matrix 2 to the 0 times, namely 1 time. And then you measure the second qubit, auxiliary qubit, and if it's a 1, you apply U twice. And you measure the third one, if it's a 1, you apply it 3 times, but if it's 0, you don't do anything. And you do this until you've gone through all of your auxiliary qubits, and now all of a sudden, your state is highly entangled, where every state, if it's 0, has a 1 in front of it, but if it's a 1, it has a phase which corresponds to the energy of the state in question. So you end up with some highly entangled state. And then you put it through what's called an inverse quantum Fourier transform, which is a well-known algorithm on a computer. I'm not going to describe it, but I'm going to mention that a discrete Fourier transform in a classical computer would require n times 2 to the n gates, while on a quantum computer only requires n squared gates. And so here you see the power of the quantum computer coming in, where the amount of operations is exponentially smaller than on a classical computer. And then finally, you do a measurement at the end here. And if you suppose you measure 1, 0, 0, 1, 1 for the values of these qubits, and then it'll tell you that theta is 1 times 2 to the 0, plus 0 times 2 to the minus 1, plus 0 times 2 to the minus 2, plus 1 times 2 to the minus 3, and so on. Furthermore, you've not measured the state you're interested in. Once I measure the spins here, my wave function collapses, and I am in the eigenstate corresponding to this eigenvalue in the system I'm interested in, even though I haven't measured it at all. It's a really magical thing, and it forces you to think about quantum mechanics much harder than you ever did in quantum mechanics class. So the only problem with this is that this method will only be a good one for finding the ground state if your initial guess had a good overlap with the ground state. That might not be very easy to do if you have a strongly coupled many-body system. So just again, to give you a feel for both how people think with quantum computing, but also how wide open the problems are and how people don't have any single solution. Here's another algorithm called the quantum adiabatic algorithm, where you have your Hamiltonian you're interested in, and you take a Hamiltonian that you're not interested in, but which is easy to solve, and you can make a linear combination of the two. You start off in the ground state of the simple Hamiltonian, and you change this parameter s, and if you do it slowly enough, you'll evolve into the ground state of your interesting Hamiltonian, and then you'll be able to make measurements on it. That's pretty cool. But there's a problem with it. Even though this is true theoretically, the question is, how slow is slow? And so what you find is that if there is a nearby almost level crossing with a gap of delta E, the time you have to take to go to transition through here is 1 over delta E squared, or else you stand a high probability of making a quantum jump to the wrong state. So what you find then is that if you have exponentially small gaps, you will have to take an exponentially long time doing this. So maybe this algorithm works, maybe it doesn't. It depends on whether you're able to construct a system with no small gaps. The third one, which we just published recently, is called spectral combing. Here's an actual simulation of a quantum computer, a very small one, where you start off in a state where the different colors correspond to the probabilities of having the different eigenstates of the system in it. So you start off with a random state with lots of excitations. You go through this thing, which is basically a resonant cooling, and you make some measurements, and you repeat, sort of like rinse, wash, repeat, and eventually you end up with a system which is all in the ground state. This is on a small system. We don't know how this thing scales for a large one. That's where all the money is. You want good scaling, because you want to beat the exponential difficulty of a classical computer. So optimal approaches aren't known. Maybe there isn't a single one. Maybe you're going to have a bunch of tools for actually solving a particular system like QCD. Some appear to exhibit exponential speedup relative to classical computers. That's the holy grail. But of course, the devil's in the details, and whether you're able to actually do it or not is not clear at this point. So will we soon be solving these really hard problems? Well, probably not soon, but it is conceivable that in our lifetimes we'll see some of these problems solved on a quantum computer. So if you ask yourself what problems would be good, easy on a quantum computer, which ones are hard, probably a good rule of thumb is to ask which ones nature is able to solve quickly. So for example, you might be able to find the ground state of a neutron star pretty quickly, because neutron stars can find their own ground state pretty quickly. But it might not be a very good way to solve for the ground state of a spin glass, which in nature will not typically find its ground state. This actually shows how much quantum computing changes how we think about physics. On the one hand, we have to think about physical reality in terms of quantum information and measurement theory. These are two things which for most of my life I swore I'd never have to know. Okay, and I thought, they hurt my head, I don't want to think about them. But now if you try to think about quantum computing, you're forced to re-examine these, and it's actually pretty interesting. Furthermore, the line between computers and nature gets blurred, such as, as you can see from this example here, where you don't normally ask what's an easy or hard problem on a regular computer by asking what's an easy or hard problem for nature. But the idea of going to a quantum computer is going to a device that operates on the same principles as nature. That actually makes me wonder whether, if you want to solve for all the phenomena of the universe, is a quantum computer enough, or am I going to need a quantum gravity computer, which has physical principles beyond which we understand right now? Well, this can lead you to the absurd, or maybe not absurd. So here is a philosopher's article. So you'd say, this is not a physics article, but this is a philosophy article which concludes that we're almost certainly living in a computer simulation. In fact, the words are even amazing. It says that we shall someday be post-humans who run ancestor simulations. So this is obviously not science. We don't know how to test it. But actually, some of my colleagues had a great idea on how to test this scientifically. Because they said, well, okay, so some being, maybe some pimply alien teenager, is simulating us right now. But if they're like simulators or computational physicists in our world, they probably have budget problems. Okay? Almost everybody who tries to compute anything knows that they never have quite enough resources. Okay? So let's suppose that the great being that is simulating us is having its budget cut and does not have enough resources and is cutting corners. Are there any ways that we can see deviations from what we expect? And so they wrote this paper called Constraints on the Universe as a Numerical Simulation, based on the idea that there might be some corners cut that we could actually explore either theoretically or experimentally. And you're in a different universe when you only get one citation but 1.2 thousand shares. Okay, so quick summary. Computational physics is far more than coding up a theory and burning CPU cycles. It forces you to understand theory in a level of profundity that goes way beyond what people with just pencil and paper tend to do. To understand a theory well enough to compute with it really means it will often lead you to far-ranging theoretical insights in the meaning of the theory you're trying to study. And I want to claim that this is a branch of physics, of science, that is vibrant and creative, and that with the advent of quantum computers, there's really a new revolution waiting for us. I hope really great, deep insights into how the world works. Thank you. I'm sorry?
You're talking about the future of quantum computers. So in the next 5 years, what do you think we'll actually be able to simulate?
Well, people, Google's talking about having a 49-qubit computer up and running. Microsoft putting tons of money in. They have a completely different approach to quantum computing. There's really no uniformity even on what the hardware is right now. It looks like the superconducting loops is the way to go in the short term, but obviously won't work for scaling for large supercomputers. Right now it's the Wild West out there. The thing that's sort of depressing is that with the current level of fidelity of qubits, when I draw a diagram showing a qubit, this is what they call a logical qubit, or I would call it a theorist's qubit. An experimentalist qubit is messy, it loses coherence, it's hard to measure, you make mistakes all the time. So you need to have error correction, and for the current level of quality, for every physical qubit, for one logical qubit, you need about 1,000 physical qubits, which is way beyond what we can produce at the moment. So right now, the hardware looks depressing. On the other hand, there's a huge amount of money going into it. So the name of the game at the moment for theorists is to use quantum computer simulators. Of course, part of the interest in quantum computing is to do problems you can't put on a classical computer, but the supercomputers now can simulate up to about 40 qubits if you go to Oak Ridge, which is really pretty impressive. And so even while we're waiting for the experimentalists to get their hardware up, theorists still have things that they can do that are interesting, because just developing algorithms is itself an interesting branch of physics.
Any other questions?
I was basically intrigued about your statement about finding the ground state of a spin-glass system. I was wondering if you got a chance to look into the D-Wave computer by Google and what you think of that. The rumor is that it's a gigantic annealing simulator.
Yeah, simulated annealing. Yeah, okay, so I don't think that algorithm can find, I don't think that algorithm can be better at finding the ground state than nature, because after all, I can make a spin glass and cool it down slowly and find that I still don't end up in the ground state. So I doubt that the D-Wave computer can do a better job than that.
Okay, thank you.
I mean, it would be very interesting if people could come up with an algorithm that nature doesn't use, maybe by adding extra degrees of freedom and some finding ways around the barriers. So I don't want to rule out the possibility that there could be ways of doing this. But I mean, to illustrate why there might be ways that people hadn't thought about on a classical computer, this method that I just showed at the very end that I'd worked on this resonant cooling, it's really just an algorithm for finding the lowest eigenvalue of a matrix. And you might say, well, why would there be an algorithm out there that hasn't already been thought about? And the answer is that the starting point is you take the dimension of the matrix you're interested in and you square it. Okay, so you want to find the lowest eigenvalue of a 1,000 by 1,000 matrix. The first thing you do is you double the amount of qubits you need, which in terms of the matrix means turning it into a million by million matrix. And nobody on a classical computer in a million years would think of an algorithm where the first thing you do is square the size of the matrix. Okay, so maybe there are things like that that never would have occurred to a classical computer physicist that you might be able to get around and find the ground state of a spin glass without making it vastly larger and adding degrees of freedom you wouldn't normally consider.
Thank you.
Any other questions? Okay. If there are no further questions, let's thank David again.